Well, this also happens, momentum and elastic collisions also conserve um, in the plane two-dimensionally. So let's say we have a more realistic example. We have this moving at velocity A, and this is sitting still initially, so velocity B. Make sure I get my setup the way I want my setup to be. And so we'll have a stationary object, and let's see, we'll put A moving into it at 4 meters per second. So VA is 4 meters per second, and we're going to make this a three-dimensional vector, or two-dimensional vector. So in a plane, so we're going to have an XY axis here, which means if this object hits like a billiard ball, this is going to go off in this direction, and this is going to go off in this direction. Right? There's going to be some directed nature to the motion. And so what we're going to do is we're going to look at the velocity vectors that come out. And we're going to see what we can get from this. So initially, let's see what else we're going to have here. We're going to make the mass. So this is what we see. We see a billiard ball coming in slowly, hits a non-moving one, and they both bounce away. This will leave with a angle of theta, and this will leave at 60 degrees above the horizontal. So let's see what happens. Well, particle A moving at 4 meters per second, initially in completely I-hat direction, nothing in the Y direction. And so this is VA. Now when they leave, we will have this going at an angle of 60 degrees. This is just particle A, collides, and it is moving at 2 meters per second at that 60 degrees, so 2 meters per second. And the mass of this is 0.027 kilograms for both A and B. Right? So we have particle coming in, hits another particle, they come off at angles. And so we're going to use the vector components to tell us what's happening. And so we're going to look at the momentum in the x direction initially is the mass of A times the velocity of A in the x direction, plus the mass of B times the velocity of B in the x direction. And initially, the B is not moving at all, oops, 0.20, my apologies, 0.20, and so 0.20 times 4 kilograms times 4.0 meters per second, and that's the initial momentum in the x direction. In fact, the whole system only has momentum in the x direction, so the initial momentum in the y direction is 0. Now these two objects are going to collide, so the final momentum in the x direction is going to be the mass of A times the velocity of A in the x primed plus the mass of B times the velocity of B in the x primed. Now the mass of A is 0.20 kilograms, and the velocity of A, well, now we know the magnitude is 2.0, so we're going to get 2.0 meters per second times the cosine of 60, because it's only the component in this direction. And then for the other component, for the theta component, we're going to get that the theta component, which is down here, is going to be dv prime times the cosine of theta. Oh, I apologize. I need my mass again as 0.20 kilograms times Vb prime cosine theta. And since these are equal, I can set these equal. And the nice thing is, I notice already all my terms are going to have the same mass. So setting the momentums in the x directions equal, I get that 4 kilogram meters per second is equal to 2.0 kilogram meters per second times cosine of 60 degrees plus Vb prime cosine theta. And if I multiply this out, well, cosine of 60 degrees is 1/2. 1/2 times 2 is 1. So I get 3.0 kilograms. Oops, nope, I divided all the kilograms out. All the kilograms get, because I divided everything out, kilograms go away. That's meters per second. Vb prime cosine theta. And so we know what the x component of this will be. Now we can look at the, let's see here, right? Because VBF is the total bit cosine theta, right? And this is the x component. So I can say that VB x prime is equal to 3.0 meters per second. Right, this defines the whole x component. So I know the x component of B now, which is one of my unknowns. The only other thing I don't know is theta. So let's look at the y components. Notice we haven't done anything mathematically new. We're just keeping track of the x and the y components, which is what vectors let us do. Alright, so I'm going to do the initial momentum in y was 0. And so now I need to add to it the momentums in y afterwards, because they're going to subtract each other, or they're going to equal each other. Now I'm going to notice that all my masses are going to divide in this. I'm going to have mass A, which is equal to mass B, times VA prime sine 60 degrees minus mass B VB prime sine theta. And let me scroll up here, try to get all these together. And so mass A equal to mass B, so these will cancel out. So VA prime sine 60 degrees, whoops, I know what VA prime is, that's 4.0 meters per second times sine of 60 degrees. And because these were separated by a negative, I'll put equals VB prime sine theta. But this is the y component. So VBY prime is equal to, and what is the sine of 60 degrees? That's root 3 over 2. So let's see. Let's see, this is in a downward direction. And let's see, the sine of 60 degrees is root 3 over 2. 2 times 4.0 meters per second. So VBY prime is 2.0 root 3 meters per second. And now what we need to do is we need to find the component to get both the angle that we don't know, the angle that B is coming in, and the total velocity that B is moving in. Since we know A's final velocity, we need to know B's final velocity. And just looking here, 0 is equal to these. I've lost my pen. Here we go. Alright, 2 seconds here, and then move over. And this is the thing I'm looking at here. This shouldn't be 4.0, right? It's A prime, which is 2.0. That was bugging me. The 2's cancel. And it is root 3 in the negative direction, because this is downwards. And so we're going to be able to say that B is going to move at this, let's see, 3.0 meters per second squared, since it's x component, plus root 3, or negative root 3 squared meters per second squared, since it's y component. We'll take the square root of the whole thing. And so what do I get? I get 9 plus 3. I get 9 plus 3. Which is 12, root 12, or 2 root 3, which is approximately 3.5 meters per second. And so we can calculate the speed. And so what we did is we took conservation of momentum and we applied it to each component. And so just like kinematics, momentum does work on the plane. And then we can take the inverse tangent. Since we have vectors, we take the y vector, root 3, negative, over the x vector. And that gives us an angle that this is moving at roughly 30 degrees. And so we have the ability, negative 30 degrees. And so we know that this is a negative 30 degree angle, and we know that this is moving at 3.5 meters per second. And we've just calculated how we do a pull shot.